Hello, everyone. Welcome to the fourth annual International Mission to Mars Design Engineering Competition for high school students. I would like to welcome Dr. Robert Zubrin, the president and founder of the Mars Society and my mentor for many, many years. It is my pleasure to be working with him, and he is going to give you, the intro to this competition. Robert, you have the floor.
Okay. Well, welcome to the design competition. This is your chance to learn a lot about the possibility of human exploration of Mars and about engineering design. Um, this is the great adventure of our time. You people are coming along at exactly the right time. I believe humans will start being able to go to Mars in about between 8 and uh, 10 years from now. And so you'll be getting out of college right about then. So you'll be prime candidates to take part in the adventure. And it is the great adventure of our time, perhaps all time. That is, this time will be remembered hundreds of years from now as the time when people first set sail for other worlds. It's like today, if you ask someone what happened in 1492, they'll tell you that's when Columbus sailed. And that's true, but a billion other things happened in 1492, but we don't remember any of that. What we remember is Columbus. And similarly, all the things that are going on now that seem very important, almost all of them will be forgotten about 500 years from now, but not the move to first make humanity multi-planetary by beginning the exploration and settlement of Mars. And Mars is the place. It is the closest world that has on it all the materials needed to support life and technological civilization. Unlike the moon, Mars has ample supplies of water. Water is only present in lunar soil in parts per million quantities, except at the South Pole in permanently shadowed craters that are ultra cold. On Mars, there are continent-sized regions that are majority water content in the soil, or even actually pure ice glaciers as far south as 38 degrees north, which is the same as the latitude of San Francisco on Earth. Okay, so there's water, there's carbon. Okay, the atmosphere is 95% carbon dioxide, and we are carbon-based life forms. And everything we eat is made of carbon, and everything we wear is made of carbon. And almost all the industrial products that we use are either made of carbon or made using carbon to make them. Okay, plastics are made of carbon, steel is made using carbon. One could go on. Mars has got a 24-hour day, very similar to Earth. Mars has all the different kinds of minerals that we need to build an industrial society. So for the coming great age of human space exploration, discovery, and settlement, Mars compares to the moon like North America compared to Greenland during the age of European oceanic exploration and settlement. Greenland was closer to Europe. Europeans did reach it first, but it was much too poor a place to settle. North America, of course, and South America, new branches of civilization could be started. So that's why we concentrate on Mars. Now, I have a book called The Case for Mars, which you may be able to find in your local public library or have the librarian order for you, or you can buy it on Amazon in either paperback or Kindle type form. It's a very useful reference for you. And there are many other references that Nicole will suggest to you as well. Because what you're going to be asked to do is design a human mission to Mars. Now, you should know that before I became an engineer, I spent 7 years as a secondary school teacher, high school and junior high, taught science. And then I went to graduate school and became an engineer. And there I encountered something that almost all engineers encounter in their college education, which is something called a design class. And a design class is different from the kinds of classes that you've had in school, and well, it's also different from almost all the classes that are given in universities too. because instead of being asked to read the chapter and then pass the test and this kind of thing, this is totally different. In a design class, okay, a group of students is asked to design something as a team. And in some cases, there are several teams and they compete against each other to who can do the best design. And within the design, okay, so for instance, in engineering, aerospace class might be asked to design a fighter aircraft. And they might be told it has to go at least this fast and at least this high and fly at least this far and carry at least this much weaponry and can't cost more than this much, and so forth. And so it has all these different requirements, and hopefully it not only meets all the requirements, but exceeds at least some of them. Okay, but this is very hard to do because in general, the different requirements fight each other. For instance, the aerodynamic requirements are going to contradict how much weaponry it can carry. And both of those things will contradict trying to keep the costs down, and so forth, and how powerful an engine it can carry. So you might have different groups, an aerodynamics group, a propulsion group, a weaponry group, a costing group, a structures group, and they each come up with, here's how we would like to design the plane, because this would be best for us. But best for us is not necessarily best for the other teams. And so you have to work out a compromise, because you can't have, if you make the plane cost nothing, no one else will be able to do anything. So it is a process of trying to find the design that is the best compromise between the conflicting requirements. Now, you are going to be asked to design a human Mars mission. You're going to be told how much. You're not going to be designing the spaceship. That is assumed. It's assumed that there is a system that can deliver, I believe it's 30 tons to the Martian surface. And you have to do an expedition within those limits. And you want to accomplish the most science that you can, okay, with the soundest engineering design. Okay, a mission that is well designed from an engineering point of view, but accomplishes no scientific exploration, has no value. A mission that looks very good from the point of view of scientific exploration, but has an unsound engineering design, has no value. So you get points for each of these two things. And so you may have to divide your team into a science group and an engineering group. And you also have to, you're going with a human team. So I think there are points for the human factors of the design, because you don't want to have the people die. You don't want to have them going crazy. Morale will be affected if you try to be too hard on the crew. So now these things are compromises. Within the amount of mass you have to deliver, if you take more scientific equipment or make the lab bigger, well, that's going to make the living quarters smaller. Similarly, if you make the engineering systems more robust by, say, making them doubly redundant, triply redundant, fourfold redundant, that's going to eat into the science equipment. And either of those things will eat into the amount of food that you can bring. And so, for example, you have a choice in how big you can make the crew, okay, but you have to provide provisions for the crew. More crew members will give you more scientific capability on the ground, but you have to have provisions for them, and that's going to go take up mass that you might want to use for, say, vehicles that will allow the crew to explore more broadly. Okay, so it is a compromise between requirements, is a good design. So you're going to be asked, okay, to choose your landing site. Okay, where do you want to go? And what is the science agenda for your mission? What is the key scientific questions you're going to try to resolve? Are you going to be, for instance, looking for past or future life on Mars to resolve that question? Or are you going to be looking for the right minerals to establish industry, so what paved the way for Martian settlement. There's all sorts of potential scientific objectives of your mission, and you want to choose the place which is most suitable for pursuing that, and you need to pursue the equipment that is most suitable for doing that. For instance, if you're going to look for life in underground water supplies, you need to bring drilling equipment. If you're not going to do that, you don't need to bring drilling equipment. You know, you'll probably want certain kinds of mobility systems. Most of the mobility systems we've sent to Mars so far have been ground vehicles, rovers, and they could clearly be scaled up into cars that people could ride. But we've also sent miniature helicopters to Mars. What about scaling those up? Now they could travel much faster than a ground vehicle and get over rough terrain, but they might not have anything like the payload carrying capacity of a small ground truck. Or maybe you don't even use a truck. Maybe you use a motorcycle. That would be a lot lighter weight, a dirt bike, so to speak, but perhaps it's too risky to travel around in a spacesuit or a dirt bike. Make the argument one way or another, okay? Or maybe a four-wheeled quad all-terrain vehicle. There's a lot of different kinds of vehicles you could use, as I say, or even a mobile lab the size of a school bus that has lots of scientific equipment in it, but might not be able to deal with the kind of rough terrain that smaller vehicles could. Okay, and the lab equipment, are you looking to do biology on Mars? So or are you doing mineral prospect? This kind of thing. And then there is the engineering design. Okay, how would you design spacesuits, for instance, to give the astronauts good mobility when they're walking around on Mars? Okay, some of the spacesuits that we used, for instance, on the space shuttle were very big and heavy, and they were great in zero gravity, but they'd be kind of heavy and stiff to try to walk around on a planet. The Apollo spacesuits were lighter and more flexible, but not as strong. And there's issues with how do you, if you're, it's one thing on the moon. We were, I think, on the moon at most a week. On Mars, we're going to be wanting a much longer amount of time, and these spacesuits have to be maintainable. Now, furthermore, how much time do you want to spend on Mars? Okay, because exploration takes time, but the longer you spend on Mars, the more provisions you're going to need, which once again takes away from equipment. So I think you can have a crew of up to 6, if I'm not mistaken, or as small as 1, I suppose. But 1 would be kind of dicey. There's no one to help that astronaut if he or she should get into trouble. Okay, I mean, clearly I go for at least 2, but maybe you want to go for the full 6. And if the astronauts that you include, you need to name their skill sets. Do you want more engineers? Do you want a geologist? Do you want a doctor? Do you want a biologist? Who in other words, you have to describe the crew, because most have 6 seats, and maybe you'll choose a smaller number than that. And you got to figure out how you can get your science program done and also have adequate support, engineering support in case systems fail, to assure the safety of the crew. You'll want to design the surface head. Okay, it has to be within the 30-ton payload capacity of the mission. But the bigger and nicer you make it, once again, that takes away from exploration equipment. But if you do have a larger crew, you can't have, a tiny habitat. So there's compromises to be made there all around. Now, I don't know if you're going to be asked to do costing on this. Sometimes we do ask the teams to do it and sometimes not. Because are we doing costing this year?
We are not doing costs this year.
Okay, so all the points are either for science, engineering, or human factors. How much for each, Nicole?
40, 40, and 20. 40 science, 40 engineering, 20 human factors.
Right, got it? Now, here's the thing. Okay, in a normal university, okay, as I say, almost every engineer who graduates college will take an engineering class, a design class of the kind that I described. And they'll present the designs to the professors and they get graded as a team. This is a team sport. However, very frequently, not always, but a lot of times, universities have contests of a team from each university competing in a intercollegiate contest where each are designing the same thing and they see which team comes up. So it's a sport. Okay, well, that's cool. Okay. And we're going to do that too. There's going to be more than one team. How many teams are we going to have, Nicole?
We have 101 students registered. Right now, we are looking at between 15 and 20 teams. Some of the team members are still filling out their time zone, so I'm still placing people. So
Okay, so maybe there'll be 6 people on your team and there'll be maybe 15 teams. So it'll be a lot of teams. Okay. Now, maybe they make the teams a bit bigger and there'll only be 8 teams or something, but we'll hear about that later. However, this is going to be a competition and we're going to try to organize it so that everybody on your team is in a time zone close to yours. That is, we don't want to have people in Singapore having to work with people in Ireland and they're up at totally different times of day. We'd much rather have people, they might not be in exactly your time zone, but hopefully not more than 2 time zones different from you. Okay, so that you can work together as a team and you can work things out. Now, we're going to do something, however, in our contest, which is not ordinarily done in university engineering design contests, but in a certain way is done in real life, that is in competitive industry, which is that there'll be presentations of the designs and you'll get to see the other people present their designs. And then the next day, your team will get half an hour to take shots at other people's designs to say, that won't work because this, okay? Or that is not the best way to do it because this, okay? So you're going to take shots at them and they're going to take shots at you. And then the day after that, you will have a half hour to answer the criticisms that have been made of you, okay? Now, and the reason why I say this is, it's not done in quite this way in industrial competition. In industrial competition, generally your competitors are trying to discredit your design and they don't do it when you're watching. They sneak around and they tell NASA, their design isn't going to work. Our design is much better. Okay, so while you may think that other teams make some unfair criticism of your design, in the case of our contest, it's a lot fairer than it is in real life because at least they're going to do it to your face. And you'll be able to answer them. Now, when you make your criticism, it's very important that you make it on solid grounds. Don't just come up with any bunk because then you'll get refuted and you'll be shown to be wrong or even stupid. So you don't want to do that. You want to go after problems in other people's designs that are real, okay, or suboptimal. That's less than best. You want to make serious criticisms of their designs, and then you want to be ready the next day to refute them. And once again, if somebody makes a criticism of your design and they don't know what they're talking about, well, you'll be able to show that. Okay, and so it's at the basis of all that, after you've had a chance to present, after you've had a chance to criticize, and after you've had a chance to defend against the criticism, okay, the judges are going to watch all of that, and then they're going to assign your team points. Okay, so that's how it works, and it's really unique, and it's a lot of fun, and it's a terrific way to learn science. Because, you know, when you take a normal class, it's like, read this and you're going to be tested on it. And it's like, well, how much of this do I really have to know for the test? Okay, you know, well, here it's like knowledge is not a burden that you have to show that you know. Knowledge is a tool. It's a tool to enable you to make a good design. And it's a weapon because it's also a tool you can use to show that the competing designs are not as good. Okay, and that's, you know, what, well, engineering education is for. It's to enable you to design things, to come up with ideas, to make things possible, and to discover flaws in ideas that would lead to mistakes. Because that's another thing that engineers need to do. They got to find the mistakes in other people's designs, both for competitive reasons, but also within the team. You don't want to be on a team that builds a bridge that's going to collapse. If there's a design flaw, you got to find it, and get it out. So both in terms of winning competitive business, but also in terms of making your engineering design successful, it's important to be able to find problems, solve them. So that's basically what we're going to do here. This is now, I think, the fourth time that we've done it, and it's a great experience, and I wish you well. And I believe that, you know, the Mars Society is going to have its convention in Los Angeles in October, and the winning team will be invited to come and present its design to everyone there.
Thank you, Robert. That was amazing. Do you have time for a couple minutes of Q&A if anybody has questions?
I sure do.
Students, if you have questions, either raise your Zoom hand or type it in the chat. Laksh Pandy, please unmute yourself and ask your question.
Hi, sir. Hi, ma'am. It's truly an honor to meet you guys. Really appreciate this. So, one of the questions I had for you, sir, is that your Mars Direct plan focuses on going to Mars using current technology, right? But if you had the opportunity to select one particular technology that would cause a breakthrough in Mars exploration, what would it be? Like, would it be nuclear? Would it be propulsion? What would it be?
Oh, well, that's a very interesting question. I believe we can get to Mars with current day propulsion. Because especially, you see, if we're talking about, well, long duration exploration on Mars. And by the way, your teams will have the option to stay any amount of time on the surface, from 30 days to a year and a half. So you can do short stays, you can do long stays. But I think surface power is very important. I think surface mobility is very important. Now, you bring up an interesting question, which is, how advanced can you make your technology in your design? And the thing is this: don't use things that are science fiction. You have to use things that are credible. Now, that doesn't mean that it has to be something you can go buy at the store today, but it has to be something that you can realistically argue could be made available within 10 years from now. Okay, so you can't use teleportation or something. Okay, none of that. Okay, but the you know, and anti-gravity machines, or all sorts of stuff. You can't even use fusion power, which is not science fiction, but unlikely to be available in 10 years. You can use nuclear power, even though there currently isn't a space nuclear power reactor. It clearly is, you know, there's been nuclear reactors since 1954, so making one suitable to use on Mars is not science fiction, it's engineering. And you do need power for your base, by the way. So you have to include that within the design. You could use solar power, you could use nuclear power. Those are the two main choices. Yeah, but the strongest engineering design is the one that requires the least technical advances compared to now. Okay. Now, by the way, you can also bring robots to help expand the exploration capability. But you can see where robots are today. You know, there are some robots that look kind of like people. There are robots that look kind of like dogs. There are just robots that look like little cars. These sorts of things can be used, but don't give them magical capabilities. You have to be realistic in terms of what you think can be available within 10 years. So this is not a mission that's going to be done in the year 2500. This is a mission that's going to be done in the 2030s. And so you can invoke more advanced technologies than are currently available or have been demonstrated, but you don't want to go too far. I mean, let me give an example. Okay. We flew a little helicopter on Mars, the Ingenuity helicopter. Okay. And, you know, it was about the size of a toy helicopter. Now, it's not that big a stretch to say, well, let's make a 100-kilogram helicopter that can be flying around with, you know, 6 instruments on it and landing in various places. I think people are quite willing to accept that such a thing could be engineered, even though we don't have it now. But, you know, do you want to claim, you know, you're going to have a rocket plane that can fly all over Mars with people and, you know, land like a Harrier jet and you know, that's not quite science fiction, but that's a big technological leap. So you can choose more advanced technologies, but there's a trade there between what more advanced technologies can do and the degree of credibility that they have in terms of, could I really have this within 10 years?
Great question. Thank you. I'm going to go to Karun next.
My question was almost the same. My question was, do we have to use current technologies or are we allowed to include technologies that will probably be available in 10 years?
Yes.
What I said, you can use technologies that will probably be available in 10 years, but don't use technologies that probably won't be available in 10 years.
Very good. And I'm going to go to Mohammed Sheikha next.
Hello, Mrs. Nicole. Hello, Mr. Robert. And
Hello.
thanks for this brilliant competition. I need to question you one question about the design of systems or designing system. Mr. Robert, you concentrate a lot about the design system or designing systems. So in our designs, we use SolidWorks, we use Fusion 360, we use all of designing programs. So the stage before this CAD design, what is the technique that can I be or that can I do it before this stage of CAD, or basically I need or I play or I use a lot of stages of designs. Example, ROS or ROS Space 2. So how can I deal with these techniques correctly? And thanks a lot.
Well, this is a good question. Okay. Well, the level of design that we're doing here is what in engineering is called conceptual design. That does not mean, well, here's my idea. It's not, we're not talking Imagineering here, okay? If, for instance, if you want to describe a habitat that can house, you know, 6 people and have a small lab and an airlock, you can kind of sketch it out and figure out how much it's likely to weigh. And you can do that with a pen and paper. Okay. You need to get to that level of design. Okay. Now, if you can go further and use SolidWorks to make a more detailed version of that, so much the better. But that is not a requirement, that's a desirement. Okay. So to the extent that you can get more detailed than the back of the envelope design, okay, in other words, that you could say, look, we initially did the conceptual design and we thought that this would weigh 5 tons, and then we put it in SolidWorks and it weighs 6.5 tons, but now we're pretty sure about that. Then you can do that. Now, by the way, that another thing you can do, because the level of design you're going to be able to do has a certain amount of uncertainty in it. Okay. Because you're not designing things down to the level of every rivet at all. Okay. Or so what you can do is you can put in a contingency mass. In other words, you say, I have 30 tons, but everything that I've specified here adds up to 25. I've got 5 tons here that if some of these things are overweight, that's my reserve that I can spend on making it as it needs to be.
Great question. I have one in the chat, Robert, and a couple other on screen, but let me ask the question in the chat from Anshika. Since landing on Mars needs us to slow down a lot, do you think plasma braking can be used to help with that? Like maybe just instead of parachutes or rockets?
Well, the plasma braking can help you decelerate from the interplanetary trajectory into Mars orbit. It can't be used to help you land. And to be clear, however, we are starting the mission here at the point when you have landed. Okay. In other words, someone else is delivering you to the surface. Okay. Now, I'll give you some constraints on that. Your HAB can't be more than 8 meters in diameter, okay, which is roughly the diameter of a starship, or the lower stages of a Saturn V or the SLS. In other words, you can't make your HAB 30 meters in diameter. Okay, you can make it 8, and you could have more than one. But basically it's you're designing the expedition. Other people are getting you there. Okay. That's where your responsibility begins. They're able to get you there with 30 tons of stuff, including your habitat, your power system, your science equipment, your vehicles, your supplies, your crew, your spacesuits, everything. And you've got to do something useful with that. Okay.
Yes. So they don't need a braking system because somebody else is taking care of that.
That's right.
Awesome. I will answer the question in the chat quickly. Since Mars isn't specifically mapped out yet, how do we know exactly where to land? Mars is very specifically mapped out. You will have access to all of that information, and you will have to decide as a team where to land. And I will explain that more later. Next question. Osama, have you asked your question yet?
No, I haven't yet.
Go ahead. Go ahead.
It's a pleasure meeting you all. Without further ado, I'd like to ask my question. What's the main points in order to consider the design sustainable or suitable?
What is the main points on whether the design is suitable?
Yeah.
Well, as I said, the fact that you're going there with an effective science exploration team and equipment that is chosen to implement the scientific objectives that you defined for the mission. Okay. Okay. And it's going to be up to you, by the way, to decide you're the first mission to Mars. What are the most important scientific tasks that you should do. Okay. In other words, you're trying to get the maximum value out of this mission. So some people spending a lot of money to do this. You want to deliver the goods. Okay. You want to give the people that are funding this mission there and the human race as a whole the best benefit you can for the effort. Okay. So you have to define what is the most important scientific goals for the mission to achieve. And then how can it best achieve it? Where should it go? What equipment it should bring? And then you have to come up with the most credible ways to do it. And, you know, if you're going to have the crew of 6 on the Martian surface for a year and a half, you're going to have to define what the life support system should be. What are the consumables you need to bring? Are you going to bring all the consumables? Or are you going to bring a greenhouse with you and try to grow some of the consumables? Which is the more efficient way to do that in terms of mass and in terms of crew time? Okay, because having your own greenhouse, well, you can get fresh food that way, but the greenhouse is going to weigh something, and it's going to take some of the astronauts' time to run it, as opposed to just taking food out of the refrigerator. So you're going to figure out what you want to do with respect to that. See, there's no answers in the back of the book here.
Right.
This is you trying to figure out how you're going to do this.
I'm going to go over with the students after your talk all of the, specifications. So if you have more questions like that, I'm going to go over what you're going to have to do here in a few minutes. So don't worry.
But you could come up with a plan, by the way. If you're going to spend a substantial amount of time, in other words, let's say you are going to spend a certain amount of time, a year and a half. Well, then you say, during the first 3 months, we're going to do this. And the next 3 months, we're going to do that. And so forth. You're going to have different phases of the mission. Okay, because for instance, you might want to map the area before you go and collect samples and so forth. And, want to figure out how you're going to conduct a scientific campaign. Okay, and depending upon the kind of vehicles you bring, you may, you say, look, we're going to land here, and we're within 100 kilometers of all these points of interest. This place, this place, this place, this place. This place is interesting from this point of view. This place is interesting from that point of view. So this is the kinds of equipment we're going to bring. This is the mobility systems that will allow us to reach those places. We don't have to, if we have a bunch of interesting places that are within 100 kilometers of our landing site, we don't need a capability to fly to the other side of the planet. We just need the capability to explore a region within 100 kilometers or 300 kilometers, whatever it is that you're trying to do.
Okay, I'm going to let Layla ask her question next, and then I have some questions in the chat as well.
Hey, yeah. Do you say the competition is about writing for realistic scientific study? I mean, with a scientific writing style and adding reference, or we should focus on creative ideas?
Well, go ahead, Robert.
You should focus on creative ideas. And actually, if you want to know, a lot of scientific writing is substandard. You should write clearly. Okay. Okay. The content is what matters, but content is best conveyed clearly. When scientific papers are not written clearly, it frequently indicates that the people that are doing the work don't really understand their work. Because if someone really understands what they're doing, they can convey it clearly.
I agree with that. Laksh, did you have another question? Because your hand is still raised.
Yeah, I did. I hope that won't be a problem.
Go ahead.
Yeah. So, yeah, my name's Laksh Pandey. I'm from India. So, what is the single biggest misconception that you think the public holds about Mars colonization, but in reality, it is not true?
Well, I think, with respect to Mars missions, the idea that radiation is a showstopper for the mission, and that therefore we have to fly to Mars very fast in order to do it. It's not true. The radiation dose level on the surface of Mars is about the same as that at the space station, and which is moderate. I mean, it's higher than regulatory levels on Earth, but in fact, we've had people at the space station for more than a year, and there's been no radiological casualties. I think that's one of the major misconceptions. You can, though, if you like, on the surface of Mars, augment the radiation protection available to you by doing things like putting sandbags on the roof of your habitat or something like that. Yeah, I would say the idea that radiation is a showstopper is one of the biggest misconceptions.
Okay, Robert, this will be your last question, and the rest of them I believe I can answer, and then we'll get to the other part of the presentation. In your video, Robert, Humans to Mars in a Decade, you said that we can reach Mars within that era with current technology, but we still haven't reached it. Why do you think that we haven't reached it yet? And what do you think, and how long will it take for us to reach Mars?
Okay, well, we've had the capability of reaching Mars within 10 years since about 1970. That is, the fundamental technology needed to send humans to Mars has been available since the time of the moon landing. Not the hardware, but the mastery of science and of technology. Now, it's better now. We can make far more powerful computers in much lower mass than was possible then. But still, it wasn't a showstopper. Okay. We landed on the moon with computers that had absolutely tiny capacity compared to what's in your phone, but we still did it. So the problem has been political leadership. We were able to get to the moon in the 1960s because we had determined political leadership that said, we're going to do this, and then mobilized the resources and stuck with it. And even though there were accidents, there was a fire in one of the Apollo capsules in 1967 that killed 3 astronauts. And we said, no, we're going. We're pushing on. We're going to do this. So they're willing to take chances. You got to take chances. Okay, now it's less risky now. We know much more about space travel. We know much more about Mars than anybody knew in the 1960s. So it has gotten safer. It has gotten easier. Our rockets are better, all that. But what we've had actually, in particular in the United States, is a deterioration of the quality of the political class. The people that got us to the moon in the 1960s were the younger brothers of the people that won World War II. They knew how to do big projects and get things done and not chicken out. Now, and they knew how to work together across party lines. Now, since then, things have not as good. However, what has happened that wasn't available in the 1960s, in addition to some new technology, is there is now private enterprise companies that are building their own rockets. There is an entrepreneurial space sector that, in fact, is advancing the technology quite fast. And this most obvious example of that is SpaceX. But they are showing the way. There's now a New Zealand company, Rocket Lab, that has sent things into space. New Zealand doesn't even have an official space program worth talking about. But okay, so in many countries, in addition to the official space program, there are now entrepreneurs who are building their own rockets and other space systems. So the reason why we didn't get to the moon, 30 years ago, is because there was only one player who could do it, which was the government, and the government became divided and incapable of doing these sorts of grand projects. But as technology advances and also as more players get into the game, it becomes possible to say, well, the US government doesn't want to do a human Mars mission, but SpaceX does. Okay. Or maybe there'll be a company in India that's comparable to SpaceX because or other countries, because what SpaceX has shown is that it is possible for a private company to do these things, and not only do them at 1/3 the time, at 1/10 the cost that was previously done by big governments. So that's why it didn't happen. I mean, the failure of the United States to follow up on the moon landing by building moon bases and then sending humans to Mars is in my view, incredible political failure. It's as if Columbus had come back from his voyage the first time and Ferdinand and Isabella, the Spanish king and queen, had said, oh, so what? We don't care about this. Go away. Forget it. And just drop the whole subject. Of course, they didn't. And therefore, Europeans expanded to the Americas. Sir?
Nothing. Somebody unmuted. Okay, so for sake of time, I would like to thank Robert. If anybody has any questions that only he can answer, please email them to me. But we've been on here almost an hour and I still have a lot of information still to go through, and I don't want to keep people here all day or night. So if anybody needs to ask Robert a specific question, please send me the email and I will forward it to him. Otherwise, if it's just about the contest, I will be answering those questions. Robert, do you have anything else you'd like to add before I go to the next portion?
Well, it's just that, I'm really glad to welcome you to this contest. This is a practice run for some of you at something you can do when you grow up and become engineers and become part of this. You are around at the beginning of a new age of humanity. You are present at the creation. It's like being there when the world is being created. In this case, a new world is going to be created, Mars. And you have a chance to be among the creators. So I envy you and I congratulate you. And so welcome and good luck on the contest. And I hope that, you're on the winning team and I can see you at our conference in Los Angeles in October.
Thank you so much, Robert. And I'm going to start answering the questions in the chat, and then I will see what the raised hands are. So Ranesh says, so other than the rocket weight limit, can we have more than one rocket coming? Bye, Robert.
Right.
Can we have more than one rocket? So yes, you have a maximum of 2 rockets. The rockets themselves, you do not have to build, you do not have to design, you do not have to consider the weight of the rocket. The only thing you have to consider is the weight of the payload. All of the supplies and people that you are bringing to Mars, that is the weight, the 30 metric tons. That's the limit. And it can only be divided into 2 total. So if you want to put everything in one rocket, that's fine. If you want to divide it into 2, you can do that as well. But that all has to be written in your plan. William said, when you say that cost is not a factor, we have to consider, should we still attempt to use realistic cost boundaries? Yes. Or do we essentially have an unlimited budget? Please keep track of your costs as much as possible. The problem with that is some things you're not going to know how much they cost. So just be realistic. You don't want gold-plated, habitats, right? That's going to weigh a lot and going to cost a lot. I answered that one. Can we use the rocket for the main components we needed to land on Mars? Can you clarify, Ranesh, I think I'm saying that right, what you mean? Can we use the rocket for the main component? Do you mean, can you use?
Yeah, hello, hi, ma'am.
Hi.
I was just confirming, as in, what if after we land the rocket and we successfully landed on Mars, could we maybe reuse the parts of the rocket, like
Yes,
like
yes,
we've built in a greenhouse like opening or anything after
yes,
disassembling the rocket? So that's
absolutely.
allowed. Okay.
Yes,
Thank
yes,
you.
you are welcome. Trisha said, say that one spaceship with humans inside actually managed to land. What is the highest danger they can face? Oh, I'm not going to answer that. I'm going to let you figure that out because that's part of the competition. You have to decide what are the dangers and how do you prevent them from being killed by those dangers. So that's part of the study that you're going to do. Answered that. Can we consider the landers from both the launches as part of our habitat? Yes. Must we consider the likelihood of accidents? Yes. Hamza, if you would like to unmute and ask your question.
Thank you for this communication and this great meeting.
Thank you.
My question is, can we replace Ingenuity helicopter with a small
What?
by
Can you repeat that? I can't
the
hear what you're saying.
robot?
I don't know if you have a good connection because I can't hear what you're saying. Can you type it in the chat?
With 6 arms that crawl inside
Oh,
caves
hold
and
on, hold on,
typographic.
hold on, hold on. I didn't hear you. You have to type it in the chat. I didn't hear most of what you said. Zoom user has their hand raised. Briefly, please. We have a lot to cover still. Okay. Karoon.
Yes, ma'am.
Please ask your question.
Sorry, ma'am, my hand was raised from the previous question.
Okay. Tame, Rustum. Unmute.
I would like to thank you for the great speeches. And my question is, does every idea we include in the report need to have a reference?
So if you are just coming up with a creative idea, obviously that came from your mind, so you don't have to have a reference for it. But if there's anything possible that could have come from another source, please check and add a reference. So let's say all of a sudden you think of putting a helicopter on Mars and you think it's your idea, but you're unaware that we already put a helicopter on Mars. Just make sure to do a search to see if something like that already existed because you don't want to get, lose points for thinking you have your own creative idea when somebody else already thought of it. Okay, Zoom user, your hand is raised. You have a question. Okay, I don't know. I think I can't hear certain people, so I am going to start with my portion of the presentation. And I would like to thank Robert again. So this is a document everyone should have seen. It is linked in the email welcoming people to the competition. If you do not have this document, please let me know. Please email me and let me know. This is the syllabus. This again will change as the days go on. So today is here. Here's the Zoom link. This is the same Zoom link for every single day. Today I am talking, Dr. Zubrin already talked, and there are 3 video links here. Mars Direct, Human Mission to Mars. I suggest you watch that as soon as possible. Mars Underground, some of that stuff is similar to what's in Mars Direct. And then this video here is a Mars presentation that links to this video, and I explain the basics of Mars. I go through and talk about all the geographical features, the water, the weather, all of the different things that are happening on Mars and about Mars. So this is a nice, brief, basic video, started in the middle where I start talking about Mars. That's a nice, brief, basic video about Mars. So you have an idea of what the planet is made of, what type of resources are there, what types of things, what types of challenges you're going to encounter. So make sure you watch that video. So today, as much as possible, watch these videos within the next couple of days. If you are already assigned a team, their emails should be on the team list. Feel free to email each other. Feel free to start talking to each other, start organizing who will be in charge of what. Tomorrow, we are going to meet 30 minutes later than we did today. So 10:30 Pacific, 5:30 UTC. We will be hearing a presentation from Professor Stephen Kane and from Dr. Chris McKay. These are both scientists who are incredibly informed on what we should do if we go to Mars. So that's tomorrow. Wednesday, we will gather together at 11 p.m. UTC. This is not a requirement on Wednesday. This is just team collaboration to ask other questions. Hamza, do you have a question? People keep raising their hand.
I am writing my questions.
Okay, thank you.
Can we replace Ingenuity helicopter spider robot with 6 arms that crawls inside caves and small places and can make topography scan?
Part of that cut out, I didn't hear all of it, but you can redesign any robot or any helicopter. Yes, you can do that. Zoom user. Okay, I don't know what's happening. Yes, go ahead.
Hello, ma'am. How are
Hi.
you?
Hi, I'm fine.
I have a small question about can we just replace the solar panels that we use in the colony on Mars with a battery that we provide with the MRO, and we can get that battery
I cannot hear what you're saying. You're going to have to type it in the chat because
dropped by the MRO
keep cutting
battery
out.
that's
Keep cutting
full
out.
of power to provide power.
I can't
for
hear you. I can't hear what you're saying. Type it in the chat, please. It's coming through robotic. Please type it in the chat. Okay, so this is the schedule. All right, Wednesday, team collaboration, we'll gather together. Thursday, 5 p.m. UTC, we have 3 talks on Thursday, 3 talks in a row. Friday, 5 p.m. UTC. So pay attention to this because these change. Monday, you're going to get together with your team on your own. We will not meet together on Monday, June 16th. Gather with your team on your own and start planning your research. All of the teams should be solidified by Monday. There should be no changes after Monday. There shouldn't be. Maybe there will be. June 17th, next Tuesday, we are meeting 2 hours later because these scientists cannot meet at any other time. So we have Adrienne Brown and Abigail Freeman. If you click these bios, you will see their biography links. Zoom user, I can't hear what you're saying when you're unmuted. You are going to have to type in the chat. I cannot hear or understand you. Wednesday, June 18th, again, we are not meeting at the normal time because these 2 scientists are this scientist, Jim Bell. This is the only time he can meet. So please pay attention to this every day. And then we'll have more team collaboration, review, and question and answer, and you will work it with your teams. Thursday, June 19th. This will be the last day we meet together. There will be one presentation and then a final Q&A and wrap up. Presentations and debates. The first round of presentation. Now we will have between 15 and 20 teams. So this is going to take a very long time. I may have to make this 20 minutes instead of 30 because that's going to be, several hours to hear these presentations. And we may have to split it up into a couple of different time periods because that's a lot of teams to hear. That's like 8 hours of presentations if you have 16 teams. So it's going to be a long day. And then you'll have 2 days to decide what are your critiques of other teams. And then Wednesday, July 16th, you will have time to critique each other. And then Friday, you'll have your closing argument. And because of the number of students, this all may change to 20 minutes, just for sake of time. So that will be prepared. Don't plan anything on those days because you're going to be here for a long time. Zoom user, I cannot hear what you're saying. I cannot answer your question. No, I can't.
Sorry, ma'am.
I can't.
Can you hear me right now?
No, it sounds like a robot. Type it in the chat. I can't hear or understand what you're saying.
I typed it already. I wrote it in the chat already.
All right, I can't. Hold on. You got to be patient. Be patient. Okay, patience.
Okay.
Hold on. Team Rustum, what's your question?
What are the key factors NASA considers when evaluating research for Mars missions?
Can you repeat that?
What are the key factors NASA considers when evaluating research for Mars missions?
Okay, that is all published. That's part of your research that you are going to have to find out, okay? So that is all published on NASA's website. So that's part of the research. Zoom user, can we replace the solar panels that are powering with a battery with high capacity and filled with energy and drop? Yes, you can do that. You just have to take into consideration the weight and what happens if the battery runs out of energy. Okay, Ruzgar, you're not on a team. Please email me or fill out this form. I'll show you right here. Got too many tabs open. If you are not on a team, this is a good question. If you're not on a team, okay, all these people still aren't on a team. Please fill this form out, okay? You have access to this. All right. Same question. Since there are so many people, is there a chance the number of people per team can increase? I really don't want to do that because then you're going to end up not having, it'll be like in school, when the teacher assigns a project and, you've got 5 people on a team and 2 people do the project and 3 people don't do the project. So I really want to cap it at 6 people. All right, next. This is the rubric. These are the instructions. This is very important. If you do not have any of these documents, I am putting my email in the chat. If you are not receiving any of these documents, email me and I will make sure you get them. My email is nicolew@marssociety.org. That is where you can get a hold of me. All right, so your challenge, design a human mission to Mars. Purpose, accomplish as much scientific exploration as possible. Your team is designing a Mars surface mission, which will include designing its habitat, surface vehicles, scientific instruments, power system, and other equipment and supplies, crew size, composition, mission location, scientific objectives, rations, duration, and an exploration plan. Keep 4 major factors in mind. Well, it's three now. Let me fix that. Used to be 4. Science, engineering, and human operational challenges. Your team should be divided up into 3 groups. So if you have 6 people in your team, you should have 2 people per group. Science, engineering, and human operations. For your team's consideration, time on the surface up to 1.5 years, so 18 months. Weight limit 30 metric tons. You have to keep track of the weight. You may split the weight into 2 separate launches. Remember, you do not have to plan the rocket or the trajectory itself. You are landing on Mars. And now what happens? Where are your astronauts going to live? What are they going to eat? What are they going to explore? What are they going to do? You have a maximum of 6 Marsonauts or astronauts. 6 people is the maximum. You can send 1 person, you can send 3 people, you can send a maximum of 6. Who should be in the crew? What are their skills and what is their training? What is their compatibility? Is there a commander? What type of spacesuits will they need? How much water will they need? How will they get water? What are they going to eat? Where will the food come from? You choose the landing site. So NASA and ESA both have many, many documents on what the surface of Mars looks like, what the best landing site is. You decide. Equipment and vehicles should take into account the landing site, terrain, and fuel type. What kind of power supply do you use? Do you bring your food or do you grow it? You should have a certain amount of redundancy among crew and equipment. For example, if you have an oxygen maker, what if it breaks and your crew can't get oxygen? You need a backup for making oxygen. The hab diameter max is 8 meters for a rigid structure, larger for an inflatable. You have to have life support in the habitat. You have to have lab space versus living space. How much space will be comfortable for the people? How much will be workspace? How will your team resolve disputes? What are your exploration possibilities? Geology, climatology, paleontology. Was there past life? Astrobiology. Is there present life? You should also think about resources for future use. What if you discover some type of precious metal while you're exploring Mars? Could that be useful for later crews? And you should consider, how do you reach the best possible overall design? This will generally include a compromise between optimizing the various features of your design. The report is due July 20th. So the designs should be written in a report format and submitted by the deadline. These will be published in a book in the future. The first 2 years are published in this book right here. If you want to buy one, it's on Amazon. These are all the previous reports. Please don't plagiarize them. You will definitely not get any points if you use somebody else's ideas. There's a 25-page limit, 12 font standard margins, 3 sections, science, engineering, and human operations. Each team member is responsible to write their own portion of the report. You may use publicly available images or draw your own. Reference information is not included in the 25 pages. And then here are the directions on how to format your paper. I'm not going to read through that. And then the first round is July 14th. Second round is July 16th. The third round is July 18th. So in the weeks between after we stop meeting on June 19th and July 14th, you will have all those days to work together as a team. Right now, I'm in the process of getting mentors for you to help each team. Hopefully, I will have enough mentors because there's a lot of teams this year. And your reports will be judged by scientists with master's degrees and PhDs who will read your reports and grade them accordingly. And because of the number of teams, it may take a couple of weeks for all of those to be graded, so please be patient. Karun, what is your question?
Yes, ma'am. Ma'am, I would just like to ask, to confirm, we don't have to take into account any of the provisions or scientific equipment or fuel for the spacecraft that is going to take us there, right? Only the return journey.
So correct. The spaceship and the food to get there and water to get there, you don't have to worry about. That's all presumed. You only have to worry about the time you land on Mars to the time you leave from Mars. So it's 30 days to 18 months. So your team has to decide.
Do we have to take into account the return journey's fuel and provisions?
No, 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 just the time on the surface. Yes. And then Lax said, can we begin working with our team from today? Yes. Now, please know there are some changes that may occur in the teams. Okay. And I have not assigned all the teams because some people are still filling out the form. So if you know your team and you want to work with them, that's fine. I'm assuming we can have multiple modules in our habitat. Yes. If so, do they have individual dimension restrictions? No. If you have a solid metal 8-meter diameter habitat, you can divide it any way you think is necessary. Some people choose to have an inflatable habitat that can be very large. It can be bigger than 8 meters because it folds up in the spaceship on the way. Ranch, I was told by my sir that I would be a part of my team, but missed to write my name. So can you add me into team 1? Can you email me that? Because when I turn this off, I'm going to lose the chat. So look at my email address, which is nicolew@marssociety.org. Email me that. I'm going to try to have all the teams done by tonight, those who are not already on a team. Okay, any other questions? Please read through the syllabus and the rubric. Please make sure to pay attention to the time. This presentation will be uploaded to the Mars Society's YouTube page as soon as it is ready to be downloaded. And I will email that out to everyone who I have their email address. Okay. Yes, you can have more than one module. Gian, yes, you have to take into, it can only be 8 meters if it's a solid habitat. If it's metal, if it's made of metal, 8 meters. You can have 2 or 3, how many you want. You just have to account for the weight. If it's inflatable, it's however much you can carry. All right. Anything else? All right. Good luck. And I hope to have the rest of those teams settled up tonight. If you're not on the team list, if you're not on a team, go to the list or email me to get access to the list. Okay. NicoleW@marssociety.org. Thank you. I'll see you guys tomorrow. Bye, everyone. Great job today.
Thank you.
Thank you.
Bye.
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 Thank you.
Bye.
Thank you.
Bye.
Bye, ma'am. Thank you.